Have you ever just sat back and wondered how your computer does it? How it can act like this master magician, juggling a dozen things at once without ever really breaking a sweat? Well, today we are pulling back that curtain. We're diving deep into the advanced execution mechanisms that make it all happen.
I mean, really think about it for a second. Right now, you might have music streaming, a bunch of tabs open, maybe a big file is downloading in the background. It all feels perfectly seamless, like it's all happening at the exact same time. But is it? That's the big puzzle we're going to solve together in this explainer. So here's our game plan. We're going to start with that multitasking puzzle. Then we'll unveil the master plan behind it all, concurrency. After that, we'll break down the 3 big techniques your computer uses: multi-programming, multi-processing, and multi-threading. By the end of this, you'll see exactly how the magic trick is done.
Right, so this magic, how is it even possible? Well, it's definitely not an accident. It's the result of some seriously brilliant computer science, all built around a few core ideas that are designed for one thing: maximum efficiency. And at the absolute heart of that brilliant plan is one single crucial concept: concurrency. You can think of concurrency as the rulebook, the master strategy that lets your operating system manage everything at once without the whole thing just descending into chaos. It's the foundation for everything else we're about to talk about.
Okay, so let's look at the official definition. It sounds a little academic, but it's simple. Concurrency control is just the art of managing multiple jobs or processes that are all running around the same time. The real trick, though, is managing the shared resources, things like your memory, files, even your printer, so that all these processes can use them without stepping on each other's toes.
So if concurrency is the what, the grand strategy, then how does the operating system actually pull it off? Well, it has a toolkit with 3 key techniques, and you've probably heard their names before: multi-programming, multi-processing, and multi-threading. Let's break them down one by one. First up to the plate is multi-programming. This is the art of the quick switch. Its whole job is to create the illusion that it's doing many things at once, and that's our first big clue that what we see happening on screen isn't always what's really happening under the hood.
The key word here, the one to really remember, is interleaved. Imagine you're shuffling a deck of cards. You're mixing them all up, but you're only ever touching one card at a time. That's multi-programming. The computer runs a tiny piece of one program, then a tiny piece of another, and another, just so incredibly fast that it all feels simultaneous to us slow humans.
And this visual explains it perfectly. We've got one chef, that's our single CPU. He's not trying to chop, stir, and check the oven in the exact same millisecond. Nope. He chops for a second, then runs over to stir the pot, then quickly checks the oven, then he's right back to chopping. He switches between tasks so fast that from the outside, it looks like all 3 dishes are cooking at the same time.
So let's lock it in. Multi-programming, you've got one CPU, its execution style is interleaved, that rapid-fire switching, and the main goal is just pure efficiency. See, if one program gets stuck waiting for something, like a file to download, that's called an I/O operation, the CPU doesn't just sit there and twiddle its thumbs, it instantly switches to another program to keep working. 0 wasted time.
Okay, but what if an illusion isn't good enough? What happens when you need real, raw, simultaneous power? Well, that's where our next technique comes in. This is multi-processing, and it's basically about adding more brains to the whole operation. The definition is simple, but the implication is absolutely huge. The game changer is that phrase, multiple processors. We're not talking about one CPU faking it anymore. We are talking about having 2, 4, 8, or even more CPUs, each one running a different process at the exact same time. This is true parallel power.
Our kitchen analogy is getting an upgrade. Look, now we have 2 chefs. One can be totally dedicated to making the soup, while the other is completely focused on baking the dessert. They are not switching back and forth. They are working in true parallel, and the result is the whole meal gets done much faster. This is simultaneous execution. So let's sum up multiprocessing. The execution style is truly, genuinely simultaneous. It requires 2 or more CPUs, period. And its main goal is just performance, a massive speed boost by tackling different programs, or even different parts of a really complex program at the exact same moment.
So we've looked at juggling whole programs and we've looked at adding more CPUs, but what if we could make a single program itself more efficient? What if we could optimize it from the inside out? Well,
That's the whole idea behind our third technique, multi-threading. This is all about breaking one big job down into smaller parallel tasks. So a process is the program itself, like your web browser. A thread is just a tiny piece of that program. For instance, in your browser, one thread could be responsible for loading images while another thread is responding to your mouse clicks. Multi-threading lets a single program do multiple things at once, which is what makes it feel so fast and responsive. Let's go back to our chef, but this time there's just one chef working on one complex recipe. Think of multi-threading as that chef using both hands for different things at the same time. One hand is stirring the batter while the other hand is simultaneously adding flour. It's performing parallel tasks within a single larger goal, making the whole process way faster and more efficient.
So for multi-threading, just remember these key facts. The basic unit of work is the thread. The style is doing parallel work inside a single program. And the main goal isn't really about overall system speed, but about making a specific application feel incredibly responsive and smooth to you, the user.
Okay, we have covered the 3 M's. Now it's time for the payoff. Let's put them all on one table to really lock in the differences and see how they all fit together. This is where it's all gonna click.
Let's just walk through this breakdown. For the number of CPUs, multi-programming is stuck with one, while multi-processing requires multiple. Multi-threading, it's flexible. It can work on one CPU or many. Now for execution, look at the clear difference. Multi-programming is an interleaved illusion. Multi-processing is truly simultaneous. And multi-threading is parallel inside a program. Their goals are also totally different. CPU utilization versus raw power versus program responsiveness.
And that brings us to the most important takeaway of all this. These techniques are not mutually exclusive. In fact, they aren't competing ideas at all. Your modern computer is using all of them, right now, together. It uses multiprocessing because it has multiple CPU cores. It uses multiprogramming to switch between all the different apps you have open. And inside each of those apps, it uses multi-threading to keep them responsive. It's really a team effort.
And all this leaves us with a pretty fascinating final thought. We've gone from managing just a few programs to managing billions of threads all across the globe. As we move into this new age of AI and the Internet of Things, with literally trillions of tasks happening all at once, how will these core ideas of switching, parallelizing, and dividing up work have to evolve? That right there is the next great challenge in computer science. Thanks for watching.